Hey, good afternoon, everybody. I hope you can hear me. I welcome you to this session on machine learning aided CFD with OpenFOAM and PyTorch. I'm going to share my screen now to show you the slides. But if you look in the discussion notes, basically, I have posted also a link there so you can access the slides also online, and they will remain online for at least a couple of weeks. So you can access them also later on. All right, before I start my talk, a short disclaimer. So the slides I'm going to show you and also a lot of the linked material is licensed under either the Creative Commons license or the GPL license. So those licenses are really non-restrictive, but nonetheless, what you should do is basically attribute where you got this material from if you consider reusing it. So without further ado, let's get started. What I'm going to talk about today is first a small overview how to combine machine learning and CFD applications. And then the main part of the talk will be about actual applications. And finally, I have just assembled a couple of lessons that I learned throughout the last years working in this field. All right, and of course, it's a training. I keep an eye on the questions that you are posting, and feel free to go through the source code that is linked on the slides and basically to ask questions about it at any time throughout this training session. Okay, so why should you consider combining machine learning and computational fluid dynamics? Well, first of all, computational fluid dynamics produces nowadays massive amounts of data. So if you consider like a modern LES simulation at high Reynolds number, such a simulation will produce data in the orders of like hundreds or thousands of terabytes. And it becomes harder and harder to actually generate some valuable information out of that massive amount of data. And then on the other hand side, of course, simulations also require data. So first of all, you cannot perform a simulation without material properties or like thermodynamical properties of your fluids and your solids, right? And of course, most applications require closure models. And even though these closure models are not always based on data, at least the modeling is guided by data most of the times. And then on the other hand side, we have machine learning. And machine learning is basically a toolbox that allows you to find patterns in data. And what it also does is basically sometimes to give you a very useful representation of your data. So these two fields basically, they complement one another quite well. So if I say data, what do I actually mean? First of all, there's the obvious data, like if you run a simulation, there's the velocity field, the pressure field, and so on in the volume, but also on the surfaces. And of course, there's also integral data, like force coefficients, for example, that you extract from your simulation. And then there is the somewhat less obvious data. So every solver basically outputs some kind of log data. And you could later on analyze that data. So for example, analyze the initial residuals or the number of iterations that your solver, linear solver took to converge. And maybe you want to find out if there's some correlation between your solver performance and maybe some mesh quality metrics. And of course, the data doesn't always have to be from simulations. You could also use experimental data, or you could just combine numerical data and experimental data. So, but how are these three different points, machine learning, CFD, and data actually combined? So the most common way I find is that first you have a simulation that produces some data, and then maybe you post-process the data into a machine learning model. And one example would be if you create a surrogate model based on your simulation output. Like a reversed order workflow basically would be that you have some data. So for example, maybe experimental wind tunnel data, and then you create a more useful representation of that data using a machine learning model. And then maybe you use that machine learning model in your wind tunnel simulation to create a more realistic inlet velocity boundary condition, just to give you one example. And of course, you can take these two workflows and stack them on top of one another. So you could consider having molecular dynamic simulations that produces some data. From that data, you extract some information like diffusivity, coefficients, or viscosity, surface tension, and so on. You maybe package those data into a machine learning model, which you can then use in another simulation on the more continuum mechanics scale, and so on and so on. You could then go to basically larger scales and create closure models. A somewhat different way of a somewhat different workflow with a tighter coupling between simulation and machine learning is the following, where the simulation produces some data, and that data is on the fly processed into a machine learning model, which is then used again by the simulation. And this goes on. And we find such a workflow, for example, when doing active flow control or shape optimization based on machine learning. So a question that I very often get from students, but also from senior researchers is like, how can I apply deep learning to my simulation? And what I usually answer them is that maybe it's not the best question to ask. And what you should be asking instead is, like, what is the problem that I'm dealing with, and can machine learning help me to mitigate that problem? And to answer the latter question, you should know what kinds of machine learning there are. And I've compiled here some very, very simple schematics that help you basically make your decision. All right. So the first large group of machine learning algorithms belong to supervised learning. And in supervised learning, we have features and corresponding labels, and we create a mapping from the features to the labels. And that's the machine learning model. So for example, consider you have some experiment or simulation. You have varied the Reynolds number, and you have measured the drag for various different Reynolds numbers. And now basically you want to create a machine learning model that represents that data. And the problem you're dealing with is called regression. So you're trying to find, in this simple sketch, the red line. What you could also try to do is that, for example, you have, again, another experiment or simulation where you have an airfoil, you change the Reynolds number, and you change the angle of attack, and you observe the boundary layer on the surface of the airfoil, and just looked like when there is a transition from laminar to turbulent. And maybe you have now collected a bunch of data points, and what you want is a machine learning model that tells you, okay, for this Reynolds number and this angle of attack, your flow is going to be either laminar or turbulent, or maybe it gives you a probability for the flow to be in either state. And the problem you're then dealing with is called classification. All right, the second large group of algorithms fall into the category of unsupervised learning. And in unsupervised learning, there are two subclasses. The first one is dimensionality reduction, and the second one is clustering. So in dimensionality reduction, we have unlabeled data, for example, the point cloud that you see here on the left, represented by two features, x1 and x2. And what you are trying to find is basically a more suitable representation, a compact representation of that data. So for example, we could now use only one coordinate, y1, that basically expresses most of the variance that we see in the data, and we can basically reduce the number of features from 2 to 1 in this little example. On the other hand side, there's clustering. And clustering is useful, for example, if you run a large parameter study, right? And there are hundreds of simulations. You want to figure out, okay, which one of those simulations went well, and which ones may be completed, but the results are somewhat off, right? And what you would do then is use clustering to group similar data points. And yeah, so would, for example, put those data into groups. Though the last large group of machine learning algorithms are called reinforcement learning or deep reinforcement learning. And what reinforcement learning basically does is that it solves high-dimensional optimization problems for you. And in fluid mechanics in particular, we find such problems, for example, when we try to achieve active flow control or shape, if you want to optimize the shape. All right, that's it for the introduction. Now let's go to the first application. And in the first application, we are going to validate some boundary layer model for species transfer. You can find all the instructions, the source code, links to the data sets that are required in the GitHub link that is put here on this slide. And basically, all you need is the data sets that are linked in the repository, and you need a Docker installation, and you can basically reproduce all of the workflows that I'm going to show you next. And of course, I should mention that this is joint work with Claire Klaassen, Irian Jerk, Professor Kuipers, and Maaike Balthusen from the University of Eindhoven. So before we get into the machine learning part, I would like to frame a little bit the problem. So if you just focus here on this Taylor bubble on the left-hand side of the slide, what you see is basically an oxygen bubble that rises in a confined channel. And meanwhile it's rising, it's also dissolving. And in the bulk liquid around the bubble, you have some copper complex dissolved. And what happens then is that the dissolved oxygen reacts with the copper complex and forms this brownish color. All right, and if you just look at this animation here, it appears like that all the oxygen is basically leaving the bubble at the rear part of the bubble. And this is actually very misleading, because if you know the flow physics of species and the species transfer physics, you know that actually the oxygen is transferred over the entire surface of the bubble, and then it's transported in a very thin layer to the rear part, and just when the flow detaches, we start actually to see it. And to show you basically how hard this problem is to solve numerically, I have here a little specimen calculation. So we are looking at a 1 millimeter bubble of water rising in, of oxygen rising in water at room temperature. The main parameter defining how hard the problem is the Peckley number, which is the product of Schmidt and Reynolds number. Schmidt number is just the kinematic liquid viscosity over the molecular diffusivity of the dissolved oxygen. The Reynolds number is the bubble rise velocity times the bubble diameter over the liquid viscosity. And for typical application, we find it in the order of 10 to the 5. Now, if you compute the thickness, the average thickness of the flow boundary layer, you get something like 45 microns. And this is already about 20 times smaller than the bubble diameter. On the other hand side, the species concentration boundary layer is again much thinner than the flow boundary layer. And the factor between the two is about 10 to 100 or even more. And what we can do on like HPCs with all the modern numerical techniques that are available, adaptive mesh refinement and so on, is something like a Peckley number of 10,000 if we directly resolve the boundary layer. Now, to circumvent this problem of thin boundary layers, people, including myself, have developed so-called boundary layer models for the species transfer during the past couple of years. We usually call them subgrid scale models, but here I would just call them boundary layer models, because sometimes people from turbulence modeling, they get annoyed and say, okay, subgrid scale modeling is only for turbulence modeling. So I will stick to boundary layer modeling here in this talk. And those boundary layer models, they really effectively mitigate this high Schmidt number problem. But here, I don't want to really talk about the boundary layer models, but rather about the question how to validate them. Because, of course, there are experimental data available, but those data are usually available only for the steady state. And only you have integral data usually. And what you really want to make sure for such models is that they are also locally correct, so locally along the surface. And what we have come up with here is basically a machine learning-based single-phase simulation approach that approximates the two-phase problem very well. And it does so much more effectively by basically decoupling the two-phase flow problem from the species transfer problem. And here's how it works in a nutshell. So basically, we start off with a two-phase flow simulation. And here, basically, the group in Eindhoven has conducted some front-tracking simulations. From those simulations, we know the position of the interface over time from the little black dots here, the front markers. And of course, we know the velocity field in the gas and in the liquid phase, and we can interpolate the velocity to the front marker points. Now, in the next step, what we are going to do is to create a couple of machine learning models. One for the rise velocity. So we take basically the center of mass velocity of the bubble and package it up into a machine learning model. Then we take the position vector of all the marker points and we parameterize them into a radius in terms of time-dependent radius in terms of the polar angle. And we also create a machine learning model for that called R hat here on this slide. And finally, we are doing the same basically for the interface velocity. So we are taking the velocity at the interface from the two-phase flow simulations, and we project them in the tangential direction onto the interface. The normal component is typically assumed to be 0 when we neglect the volume effect of the mass transfer. I should mention here in addition. So we have now 3 machine learning models. And why do we need those models? Basically, what we are going to do next is we create a single phase simulation that contains only the liquid phase, and the gas phase is basically cut out. And this basically introduces a new surface for which we need boundary conditions. And what we do in the single phase simulations is that basically we use the machine learning models to provide an accurate boundary condition. So the radius basically tells the OpenFOAM solver how the mesh deforms over time. And the model for the velocity provides a velocity boundary condition. All right, here's basically, in a nutshell, how this is implemented. If you go to the repository and follow the notebooks that are available there and the OpenFOAM setups and boundary conditions. So first we extract the data from the two-phase flow simulations. This has been done already. And then there are some notebooks that basically load the data, do some initial processing, extract the features, and of course, very important, you just have a first look at the data. Then we train the machine learning models. Here I used like some very simple neural networks, basically the simplest form you can use, and they are implemented in PyTorch. Then we take those models, we export them to TorchScript, and basically TorchScript is an intermediate format for the models that allows us to exchange models between different front ends of PyTorch. So basically we can create a model in Python, save it to disk, and then load it in the C++ environment. for example, if you want to compile OpenFOAM boundary conditions. Oh, so then we implement a boundary condition in OpenFOAM, compile it, and then we use it in the simulation. And during the initial part of the simulation, the boundary condition will just load the different models from the disk and then run the simulation. And to give you a small feeling how this looks like, I think there was a question. Okay, is the ML model trained on many simulations with different operational conditions? No, that's not the case. So basically, we performed a small parameter study with different Reynolds numbers and different, yeah, so that's it basically, different Reynolds numbers. And I created separate models for each individual simulation, basically. You could have also tried to create one model that also has the diameter, like some kind of equivalent diameter as input feature. But yeah, so this would have made the training unnecessarily complicated. All right, I hope this answers the question. Okay, and here is basically a small trick that I have learned during the past years, how to create very nicely packaged models. So basically, what you have to do during the training process is to take your training data, to rescale it to maybe the range 0, 1, because your models are scale sensitive. And then basically, whenever you have to evaluate run forward path through the model, you need to take the features coming from the simulation, then you rescale it as the training data was rescaled, then you run the forward pass, and then basically you have to scale it back to give it data or labels in the right scaling back to the simulation. And like initially, I have basically created this rescaling in OpenFOAM, but actually it's much nicer if you package everything up into this little class here, which is also a PyTorch module. And this is also nice if you just want to combine several smaller models into one top-level model. All right, and here's how the results look like. So as mentioned before, we have different Reynolds numbers from left to right increasing, and the left half of each picture is basically the two-phase flow simulation where you have the gas phase, and the right half is the machine learning-based single-phase simulation. And what you see is that we have a really good agreement, and basically we can run the single-phase simulation at a fraction of the cost of the two-phase flow simulation. And we can also massively refine the single-phase simulations, especially close to the interface, to really resolve the species boundary layer directly. Now here's an example of how this looks like. Here just physisorption examples at Schmidt number of 100, which is already quite realistic. And we can now basically extract all the different data we need for validation from those simulations. Here I have another animation where I just zoomed in at the boundary layer. You see this is like 80 times enlarged around the equator. And you see basically how the boundary layer is changing over time as the bubble accelerates, because our inlet velocity is time dependent, right? And how we always have some cells in the boundary layer, so to resolve the boundary layer properly. All right, and another nice property is basically that we also have a very low mesh dependency. So if you just repeat the simulation with an even denser mesh, you get very much the same kind of global mass transfer expressed here as the Sherwood number. All right, and now you might be wondering, okay, do I really need all this fuss? Can't I just use, for example, a free slip boundary condition for the bubble surface? And the answer is not really. So especially during the initial transient rise of the bubble, like a free slip boundary condition will just give you much worse results, and those data are not really suitable for validation then. All right, this concludes the first example. And in the second example, we are looking at an unsupervised learning algorithm, and we will use that algorithm to find coherent structures in the transonic flow on a NACA 0012 airfoil. Again, the source code is available in this GitHub repository, which is a small software library that I'm developing. And basically, what I'm going to show you is part of the tutorial collection of FlowTorch. If you click here on the link on the basically right side of the slide, you can download the surface data that I'm going to process in the next couple of slides. There are basically two ways to access the data and everything that you need. The first one is more dynamic. So you just clone the repository, you build the Python wheel, and then you install it using pip. You navigate to the documentation and in particular to the notebooks directory, and you fire up JupyterLab. If you prefer to have like just a static access to look at what is in there, you can download the documentation here, the HTML documentation under this link. You unzip it and you open the index.html in your web browser. And finally, the tutorial is actually called DMD analysis of airfoil surface data. I should also mention that this is, of course, joint work with my boss and group leader, Richard Seemann. And this is work that we are conducting within the DFG FOR 2895 project. So what is actually a transonic buffet? If you look at an airfoil at transonic flow conditions under certain angles of attack and Reynolds numbers, what you will see is that shock forms on the upper side of the surface, and this shock basically moves rapidly back and forth. And this motion, this unsteady motion, is called a buffet, or a transonic shock buffet. And the scientific question we want to answer here is basically, is there some kind of connection between the shock oscillations and the separation of the boundary layer that we saw close to the trailing edge of the airfoil? And the machine learning technique we are going to use here is called dynamic mode decomposition. So before we actually go to the surface data, I want to show you a very quick and easy example to show what the DMD does for you. So what I have here is a simple one-dimensional profile that changes over time. So you have some spatial component that is multiplied with an e to the power of some imaginary number times the time. So what this imaginary number does is it gives it the entire profile like a sine or cosine-like change over time. And if you compare this blue markers with the orange markers, in the orange markers, the imaginary number has a real component. And what this does is basically it causes the signal to become weaker over time because the real part is negative. Now let me show you another simple profile function. Here we just have this line that is basically whipping up and down at a different frequency, and a third profile. Here basically you have some tangents hyperbolicus over cosine hyperbolicus. And again, the profile is changing over time, of course. And if you look at the orange markers, here we have a positive real part of the imaginary number. And what this causes is that the signal is basically growing over time. All right. Now, if we superimpose all these three functions, what you get is this line indicated by the blue markers, which already looks quite complex, even so we used simple functions to build it up. Now we can, because this is a simple one-dimensional example, we can basically roll the temporal evolution out, and we get such a surface plot, for example, right? All right, here's how DMD works in a nutshell. Don't worry too much if you cannot really follow along here. There's an introductory notebook in the documentation that gives you some more background, some references to start learning about the DMD. All right, so we start first by organizing our snapshots in data matrices. And in those data matrices, basically each column is composed by one snapshot. And the difference between X and X prime is that X prime is basically shifted by one snapshot in time. So it basically starts at the second snapshot and ends at the last snapshot. And the X data matrix starts at the first and ends before the last, basically. And in practice, actually, we do not really have two data matrices, but we rather work with two different views on one data matrix. Then in the next step, we compute a singular value decomposition of the data matrix. And what this allows us to do is basically to approximate a best fit linear operator that basically takes a snapshot from time t and transforms it into the state, the next state at t plus delta t, basically. And then we compute the eigen decomposition of that approximated operator. And based on the eigen decomposition, we compute the so-called POD modes. And what those modes are is actually like coherent structures, spatial structures that are coherent in time. And what we do in the DMD is to approximate the temporal evolution by a superposition of those spatial DMD modes. All right, so here's an example of how the DMD modes look like for the simple example that we looked at before. And you see basically each mode represents or is representative for one of the functions that we superimposed to create the input data. And what the DMD also provides us with is like the information about the time dynamics for each mode. So we get an amplitude and a frequency for each mode. So now let's get back to the surface data of our buffeting airfoil. And what we do here in this analysis is that we first load the pressure coefficient on the airfoil's surface, and then we use that to assemble the data matrix. So here in the top of the slide, you see basically one such snapshot. And this data is now two-dimensional, basically, but we still do the same processing. So we just take all the sampled points, we ignore their like spatial relationship, and we just put them in a very long column vector of the data matrix. The next step is then to compute the singular value decomposition to look at the singular values. And this tells us basically where we have to truncate when computing the linear operator. And FlowTorch comes with a small and simple class to compute the DMD for you. And it provides you also access to like frequencies and amplitudes, the DMD modes and whatnot to analyze them. So here's the example of the surface data of our buffeting flow. And what I've done here is to plot basically the amplitudes of the individual modes over the associated frequencies. And I should also mention that the modes, the markers here are scaled with the mode's magnitude. So basically, if a marker is larger, then the mode contains more variance. And the vertical lines here are basically indicate the buffet frequency, which I extracted from an experimental paper, and multiples of that frequency. And what we are going to do next is we are we are going to pick out some of these modes based on the size of the markers and their location, and we are going to analyze those modes. So here you see, for example, the modes 1 and 13. They're really close to the buffered frequency, and they're also rather large. And there are also some other modes that would be interesting to analyze. Okay, now let's look at those modes in a bit more detail. So the first mode here on the top, this is basically the zeros mode. This is some kind of steady mode that does not change over time. It's usually similar to the mean. Now below that we have the modes 1 and 13 that we picked out before. And what you see here is basically that there's a strong correlation between the region around the shock and the region where the boundary layer separates. So basically we know now that those two regions, they change periodically over time with the same frequency and a similar amplitude. So basically when here around the shock the pressure drops, then in some parts here of the boundary layer close to the trailing edge, the pressure rises at the same frequency. And basically the modes 13 and 1, they look fairly similar. And this is because of some shortcoming of the DMT. So basically all SVD, singular value-based algorithms, they have a weakness when it comes to translating structures in your data. And unfortunately, the buffered is such a structure. So it basically moves back and forth. And what this creates is basically, this kind of shifted mode. And I have just covered basically surface data here, which you can load simply using pandas. I think there was a question, right? What criterion is used to truncate the SVD? That's a very good question. The modes are not sorted here. So basically, you could then do some additional analysis, basically picking out important modes, for example, using sparse DMT. This I haven't done here. So I have just picked out modes based on a meaningful physical frequency. And the SVD here is truncated based on something called singular value hard thresholding. And there is basically, so it's determined automatically based on some criterion. And if you go to the notebook, the article and also some other tutorials are linked where you can look up how it's truncated precisely. I think in this example, basically, we truncated at 47 or so, 49 modes, something like that. I hope this answers your questions. And okay, so basically what I wanted to mention is that, so in the example here, I loaded the data using pandas, but FlowTorch basically provides you also very easy access to field data of OpenFOAM. So there's a class code foam data loader, which just takes a path to OpenFOAM simulation, and then it gives you access to the available write times, and you can also load mesh components. You can mask the mesh basically, because usually if you perform SVD or DMT analysis, you don't want to take the entire mesh, but only a small portion of it. And then basically you can load the snapshots, for example, for vorticity at a certain time step, and apply the mask to it. Everything in one line, very easily. All right, this completes the second application. And the last application is maybe the most interesting one. So here we are trying to achieve active flow control based on deep reinforcement learning. And again, everything is available in a GitHub repository. this time a repository of my student, Darshan Tumar. And so basically, this is a tutorial you cannot really execute on your PC unless you have a really powerful workstation. But it requires some more power, basically. So nothing to do on your laptop. And yeah, I should mention the results were produced by Darshan, of course, during his bit off topic. Okay, very good question. So basically, the loader is entirely implemented in Python. So it doesn't basically take the OpenFOAM mesh class, for example, and create a binding from C++ to Python, but it's just entirely implemented in Python. All right. So yeah, this was part of Darshan's Studienarbeit, like a small student project, something in between a bachelor and a master thesis, which he conducted at our institute. And if you click on this link here, you get to his report where you have some write-up. Please keep in mind, it's just a student report and it's not a scientific article, so there might be still some small flaws in it. So as a first example application, we have basically picked the most challenging problem that there is in computational fluid mechanics, and maybe in fluid mechanics in general, the flow past a circular cylinder at laminar flow conditions. So we have basically this nice vortex shedding behind this cylinder. And the scientific question is now, can we rotate the cylinder to stabilize the flow? And in particular, can we just take some data from the surface of the cylinder and basically predict the rotation to stabilize the flow? And the deep reinforcement learning algorithm that we used here is called proximal policy optimization. So reinforcement learning in general works in the way that we have an agent, and that agent is interacting iteratively with an environment to achieve a certain goal, which is basically defined by a so-called reward function. Now, in practice, the agent is basically some software application that reacts, in our case, with a simulation and manipulates that simulation in order to achieve a certain goal. In our case, we want to basically reduce drag and lift as much as possible. Now, one particular attribute of PPO is this very nice feature that it allows us to run or to use multiple environments, multiple simulations in parallel. And this enormously accelerates basically the entire learning process. And the way how the control works basically is that in each simulation, we have a boundary condition that takes, that samples pressure values from the surface of the cylinder. Then these pressure values are fed into a policy network that basically predicts the angular motion for the next time step. This is how it works in a nutshell. And you might be wondering, okay, so how is this algorithm actually exploring the parameter space? And the answer is depicted here on this slide. So actually, before when I said we predict the angular velocity, this was not 100% precise. What we actually do is we have the network that takes in the state, or actually an observation, so our pressure values from the surface. Then we run a forward pass, and the output of the network is actually the mean and the standard deviation of some probability distribution for the angular velocity. So basically, to predict the angular velocity for the next time step, we sample a random angular velocity from a Gaussian distribution, at least during the training phase. And this is how basically, by iteratively interacting with the environment, the reinforcement learning algorithm learns to control the environment to reduce drag and lift. The reward function is formulated as follows. Of course, we have drag and lift in there. And what we also included is the angular velocity, of course, and the angular acceleration, because we want the controller to be rather efficient. And basically, each of these terms is then multiplied with a weighting factor, to give them different weight in the optimization problem. And we take the negative of that because usually reinforcement learning problems are posed in a way that we want to maximize and not maximize the cumulative, the expected cumulative reward. All right, so how is this actually implemented? Let me see if there's a question. Okay. So on the one hand side, we have a Python script, Python and PyTorch, and this script creates our networks that we need. So there's a policy network and there's a value network. The value network basically is only used to stabilize the training process. And then in the next step, we fill our buffer using with trajectories. I tell you in a second what trajectory is in detail. So basically, this step performs now a bunch of simulations. Then in the next step, we evaluate the trajectories from the simulations and compute so-called discounted rewards. So basically, we analyze how well we did during the last iteration. Then we use a special policy and value loss function to update the weights of our networks to get a little bit closer to achieving our goal. I have not put the loss functions here in the slides because they are rather complicated. But if you go to the material and to the report, you can basically find the linked articles where this is explained in detail. So it's not a simple like L2 loss function or something like that. But there's a lot of clipping and many tricks learned that people have learned over the years. And basically what you do next is you repeat this iterative cycle until you achieve your goal, or until basically the rewards stop increasing. Is there an integration plan with the Python code Herv Yazak talked about? I haven't. I'm going to follow the talk for sure, but yeah, I have too little information to make any statement about that. All right. Okay, another question. Is the ML model trained? Ah, no, okay, this was an old question. Okay, so the second part of the implementation is now OpenFOAM related. And in the OpenFOAM, so there's another question. Okay, stabilization of flow past the circular cylinder. Did you compare the ANN-based approach to the standard projection-based model order reduction in system control? For example, the work by some authors, especially with respect to computational costs of surrogate model generation and controller robustness, speed of convergence, and so on. No, we have not done any comparison. There are some works now out on basically reinforcement learning based flow control. And the most complex problem, so to say, that I have found so far is basically a pinball problem. So very similar to what I show you here, but just with 3 cylinders basically. And so to be precise, I have not seen any comparison yet. I have not done any comparison myself. But of course, I think this is not only on my plan, but also on the plan of many other researchers to compare the different types of learning strategies. Also, for example, comparing reinforcement learning based learning to something like genetic algorithms, for example. But what I can already tell you, what I hope to achieve with deep reinforcement learning is basically to create controllers that are much more efficient, and to create also controllers that are applicable to more complex systems. And I think, so there's no really proof of some real application yet, but I think like reinforcement learning is a tool to achieve basically effective closed loop flow control for really complex problems. Have you also tested using decision tree based learners? No, I haven't tested anything like that. All right, back to the slides, as long as there are no further questions, but like I like your questions, please keep asking. I also like the reference here that you posted. I'm definitely going to have a look at it for sure. Okay, so on the OpenFOAM side of things, we have a velocity boundary condition. That boundary condition reads the policy network to make predictions. And then during the runtime of the simulation, every once in a while, it will sample pressure values from the surface and then apply the sampled action, the sampled angular velocity as a boundary condition. And then over time, it will basically keep track of the pressure values on the surface, so the so-called state in reinforcement learning speaking, then the action that was taken, and also the reward that we received. In the actual implementation, the trajectory only contains basically the state and the action taken. So basically a trajectory is nothing but a collection of state action pairs. All right, here's how it looks like if you look in the 0U file of the test case. So basically we have a couple of geometrical parameters to define how the cylinder is oriented. Then the model, the policy network, is just loaded by defining the string where the model is located, the location of the model as a string. We can set basically the start time. During the training, we will just like prescribe this controller more robust to the state in which the control actually starts. We can set basically the interval, like how often, after how many time steps the policy is basically evaluated again. And finally, there's a Boolean switch to switch the training on and off. So basically, if train is true, then we will sample our next action from the Gaussian. And if train is false, then we will just take the mean value. All right, so here, this is how it looks if you run a couple of PPO iterations. So each iteration here like comprises now, I don't know, 10 or 20 different simulations of our cylinder setup. And you see after about like 50 to 60 seconds, the mean of the rewards basically stops changing. And we would consider now this learning process as completed. So here's how it looks like in terms of the temporal evolution of the drag coefficient. So what you see here, the dash dotted blue line is basically the uncontrolled flow, the drag in the uncontrolled flow. Then the orange dotted line is basically an open loop controller, which we designed and optimized. It's just like changing basically the angular velocity in a periodic way with some, like according to some sine function with an amplitude and a frequency amplitude and frequency we optimize basically by just running a parameter study. So just to give you some background what this orange line comprises, and the solid green line is what the closed loop reinforcement learning based controller achieved. Okay, there's another example. How much computational resource is required for this training process in the example? So of course, this is like a friendly example, like a single simulation takes about half an hour on a single core, I guess. I think it was, yeah, performed on a single core. And basically, so you run 20 simulations in parallel. This means basically you need about, if you have 20 cores available, you need about 50, 60 times half an hour. So 2-3 days, and then the training is completed. Let me see if there's another question here. Okay, so now what we see from this plot here is basically that first of all, both open and closed loop control reduce the mean drag quite significantly, about 5 or 6%. But what the closed loop controller also achieves is basically to significantly reduce the drag fluctuations and not just the mean. And if we now look at the angular velocity that is basically imposed during the simulation, we see two effects here. So if you look at the orange solid curve again, this is the closed loop reinforcement learning controller. So first of all, it controls much less in terms of amplitude and also frequency. So if you convert this to a real application and you consider power consumption, this controller would consume much less energy, basically. And another interesting effect is that if you look at the mean, if you eyeball the mean of this curve, it's not 0, but it's positive. And basically what this means is that if you put a marker dot on your cylinder surface, and then you observe how the cylinder rotates, it basically keeps spinning in one direction. So it sometimes stops and turns around, but on average, it moves basically always in one direction. And this is an interesting effect because it's related to the simulation setup. So the cylinder flow that we used is basically an old benchmark, based on an old benchmark paper from the 90s. And the cylinder is placed slightly off the center, like just a tiny little nudge. And this causes the flow to be slightly asymmetric. And basically our controller picked up this missing symmetry and keeps rotating in one direction. What is the lift then? I guess it will be positive. The lift is close to 0. Unfortunately, I haven't included it here, but if you go to the report, there's like for many different examples, there's also the lift included. And what this just triggers is that, interestingly, if you leave out the cost of the rotation in the reward function, what happens then is basically it tries to spin very quickly in one direction. And this is also basically in the open loop control the case. So basically, if you spin the cylinder very rapidly in one direction, there's some Magnus effect, which basically allows you to completely reverse the drag. And but then, of course, the lift goes up enormously. But in this case, the lift is close to 0, actually. All right, let me see if there are more questions. I think that's not the case so far. All right. And actually, that's already the last slide I have here for this application. And like finally, I have compiled some, random, more or less random lessons learned, just some things that I consider important. Yeah, so it might be not perfectly zero, but it's close to zero. So there's a question in the report. It seems that the average of CL is not zero, which is probably due to the asymmetry you mentioned. So yes, also in the base flow, basically with natural vortex shedding, the lift is not exactly zero. And I should also mention that you could tweak a little bit the behavior by changing the constants in the reward function. And currently, with the currently selected parameters, the drag just has a much higher weight than the lift. So you would have to improve the controller much more to get the lift basically really to zero, I guess. All right, some lessons that I learned, not really in any particular order. So I think they're all important or not important, depending on what you're doing. Okay, there's another question that I maybe missed before. How do you define constants in the reward function? That's, again, a very good question. The constants, basically, in the reward function, we have taken partially from literature. So let me quickly go back to show everybody what we are talking about. So basically, the constants R1 and R2, we have just taken from literature, from other experiments. And these terms we have just, picked by eyeballing the magnitude of these terms in the simulation. But we have found that, so the last two terms, basically, they're not really sensitive to the particular constants that we chose, basically. And the other two constants, R1 and R2, basically, yeah, so there's also some range in which the result is relatively robust to those constants. I have to say, we took the constants from other articles that actually had a different mechanism of actuation and also use different kind of sensor information. So most of the other articles use basically pressure values from the wake of the cylinder. And for example, in terms of actuations, they use like small liquid jets on the surface of the cylinder or also rotation. And yeah, so basically the features and the actuation is a little bit different in this example, but still we could, just take their constants and apply it to our optimization problem. So I guess there's some robustness in this terms, in picking these constants. All right. Let's see if there are further questions that I may have missed. Guess not. Okay, let's go back to the lessons learned. Oh, yeah. So first of all, for many applications, it's tricky to find good features that are basically that allow you to create effective models. And what I can recommend is basically to use as much as possible, like physical relationships that that are available for your problem domain. And instead of like deciding for a certain feature, you should just like extract as many features as possible, and then use some automated feature selection tool to pick the most important ones. So usually, for example, if you use ensemble learners, they have some kind of metric to give features like a value. And what you can also do is use something like sequential forward or backward selection, just to give you some examples. And what is also surprisingly difficult sometimes is to really be sure that the features you are training your model with are also available in the application that you target. So to give you like a concrete example, let's say you have a swarm of fluid particles, and now you want to create a data-driven model for the drag of those particles. Now you can imagine that you can probably find a good correlation between the drag of a single particle by from knowing the position and the distances of the surrounding particles, right? Now you could probably create a machine learning model that predicts you the drag based on the neighboring position with a high accuracy. Now, but if you want to use such a model, for example, in an Euler-Euler simulation, this would be like impossible, because there you only have like mixed properties, and you do not really know the position of individual particles. So this is maybe like an obvious example, but it can happen easier than you think, that basically you will train on some features that you do not really have in your target application. Right. So the next lesson I had to learn the hard way was basically that you should always think first what kind of mapping you actually need, and then learn that mapping directly. And just to give you a small example here, I hope some of you know basically how Pole functions in turbulence modeling are implemented in OpenFOAM. So basically what you do there is you take an analytical relationship coming from boundary layer theory. So for example, Spalding's function, this gives you a relationship between y plus and u plus, so that a dimensionless distance to the wall and dimensionless velocity. And then what you usually do is that you find the shear stress velocity, u tau, iteratively based on the cell-centered values of y and u in the first cell at the wall, basically. The shear stress velocity to correct the shear stress, because basically, you know, your mesh is not dense enough to really resolve the gradients, and you have to make some corrections. And in OpenFOAM in particular, you are basically overriding the turbulent viscosity for the patch. Sorry. Now, what I have done, and what you could consider doing, is basically, of course, first to collect the boundary layer data to create your machine learning model, and then to create a model basically that just replaces the analytical profile function that you used before, and then continue the process as you did before, basically, you know, finding u tau iteratively and then correcting the shear stress. But actually, what you can do with machine learning is to take a shortcut and learn directly the mapping from, for example, the cell-centered, the velocity at the first cell center, and predict based on those values the shear stress and compute the correction from that. So this now, again, this may seem obvious, but yeah, it took me a while basically to see that. And what's also another example maybe, so for example, if you want to predict the drag of an airfoil, right, instead of learning the entire flow field around the airfoil, basically, and then from that to infer the drag, try to go first the short way and just predict the drag directly. And if you want some more intuition why the drag looks how it looks like, then maybe like learn a mapping from the surface to the drag and basically use that. So just to give you one more example. All right, another point here, like remove as much of the variance from the data as possible before you start the training. So one example here would be, so if you just learn relatively simple functions, right, you know that your analytical solution, asymptotic solution, whatever you have, is rather limited, and now you want to replace it with a machine learning model, right? So instead of maybe replacing the analytical model with something that you learned purely from data, it might be much simpler to basically learn the deviation from your asymptotic or analytical solution than basically learning the entire mapping. And another trick that makes learning much easier often is to combine multiple models instead of trying to learn basically directly the master model. So combining means that you can maybe decompose spatially your domain if you learn something, or you can also make this model combination in the temporal sense to have basically models that act at different times, just to give you one example. Let me quickly check if there are more questions. Not the case now. Okay. Another lesson learned. Yeah, so most of the times the actual machine learning algorithm that you use is not really that important. If possible, keep it simple and of course use what is easily accessible for you. If you already have, like, I don't know, a binding to a library, then use the models from that library or try to use that models first. And instead of, fixing yourself or being too fixated on like one particular model or class of models, just use scikit-learn or a similar library, create a pipeline that tests a bunch of different models and the corresponding hyperparameters for you, and then you just pick the best model. Okay, there was something happening here. Is there an application paper of a data-driven wall function that you can refer to? So yes, I have done work in that field for a couple of years now, but I have mostly focused on basically not wall models, but boundary layer models for species transfer. But like the principles are very much the same. And I have also just seen recently on Google Scholar that there are papers, or that there was one paper creating an LES wall function for wall modeled LES based on machine learning. Okay, there's another question, but what is the advantage of learning tau W instead of U+? So basically it's more direct. So you're not really interested in U+. What you actually want to know is the shear stress at the wall. So basically you save the entire iterative inversion of your relationship and stuff like that. So you run a forward pass, for example, through your network, and you directly get the correction that you need instead of having this iterative process in between. How difficult will it be porting this to SU2? I'm not sure, maybe this was a question related to another slide. I'm not really sure what this refers now to. But like, just to come back to the previous question, basically, if you follow some of the links there, you find references to my PhD thesis and some other papers I have written about data-driven wall functions or boundary layer models, let's say. All right, let me quickly scroll through the questions, see if there's more that I have missed. All right, seems not the case. All right, where were we? Okay, yeah. So from my experience, really, like simple neural networks, multi-layer perceptrons, often a good algorithm, just if you don't know how hard the problem is going to be. Because they are like generic function approximators that are really flexible, and thanks to the frameworks like TensorFlow and PyTorch, it has become really easy to create such mappings. Now, if you decide to use deep learning tools, neural networks, another lesson learned is that basically the architecture for most applications is not really that important. So what you should do is like find a good baseline model that gives you by trial and error that gives you a somewhat good approximation. And then again, use some pipelines, some automated scripts that do hyperparameter optimization for you. There is something, if you go through the literature and search for automated or automated ML, AutoML, yes, you find like libraries how to do that. What you can also do is basically very easily build mathematical constraints into the network's architecture. So for example, ensuring that your model is bounded to a certain range, this is really easy. And so on this little picture here below, you basically see a little parameter study. So NH is the number of hidden layers of your neural network. The NU is the number of neurons per layer. And what you see here is basically the L infinity norm for a rather simple approximation problem. And what you see is basically if the network has a certain capacity, it doesn't really matter which set of exact architecture parameters you pick, but your model will always perform quite well. All right, next lesson learned. Really important, please don't just rely on the L2 norm that you get like from your loss function or maybe the R squared score, because very often if you have a lot of data and the data is not homogeneously distributed in the feature space, those metrics, they are not really meaningful. Yes. So one metric that you should check at least is the L infinity norm. So always check like the maximum error. And what is also really useful to see maybe how to split up your model or what actually makes the training stop, for example, is to first of all check how the error is distributed. So there might be only very few points that have bad accuracy, but it could be still bad for your application. And if you have those points, then have a look at the feature space where those points come from, or where those points are located in the feature space. And here are two examples. So this is basically a link you can also follow. Okay, there's another question. As you mentioned, we can use machine learning as a surrogate or for some part of the solution. How do you think we want to use it as a surrogate for the whole solver? What are the issues? I will come back to that question maybe at the end of my lessons learned. So be patient for a second. Just to come back now to these little figures. So here on the left-hand side, basically you see the error in our labels that we try to predict. You see it's, roughly speaking, a Gaussian. So most of the training data has almost zero error, but then there are some with larger errors. And if you now look at the two main features, in this case, this is some kind of average concentration, and this is some normalized distance from the surface, right? And this heat map basically shows you it expresses the L infinity norm of our label. And what you can basically see here nicely is that, so if the average concentration becomes, normalized one, I should say, becomes large, and at the same time, the distance is rather low, then basically we get the highest error. So our model is not performing very well in this region here, right? And now this can give you some intuition, basically, maybe how to split up the model, like how to use a different normalization, stuff like that, to improve the model's accuracy. And another really important lesson, I titled this, treat your, like if your model training includes nonlinear optimization, like treat it as an experiment. So what I mean is that you should respect that there's uncertainty in the outcome of your training process. And what you would usually do if you conduct an experiment, right, is that you just don't do it once, but because there's uncertainty, you repeat it multiple times, and then you look at statistical quantities. Like, first of all, you look at the distribution. Is it more or less Gaussian, right? Then maybe you compute the mean, and this is what you finally report. And really, you should do exactly the same when you benchmark machine learning models that include some nonlinear optimization. So, for example, right, if you have a neural network and you use, instead of activation function A, you use activation function B, you shouldn't just like perform a single training loop and say, okay, activation function A leads to smaller loss values than activation function B, but you should repeat this experiment, if possible, like 100 times, look at the distribution, and then report the statistics. And a really nice way to represent those uncertain outcomes is basically to create a box plot. And the box plot basically gives you information about outliers, about the mean, a little bit about the distribution, if it's normal or not, more or less. And you can follow the links here on this slide to learn more about it. And yeah, finally, to come back to your question, I would suggest basically, if you have classical solution approaches available for your problem, then rather use those than like switching everything to machine learning. So basically, if there is not any particular problem why you would want to replace your CFD solver with a machine learning model, then I wouldn't do it, basically. If that answers your question. So maybe you are thinking about something like physics-informed neural networks, right, to replace CFD solvers, for example. I think this is not going to happen because pins just have too many disadvantages, and it's unlikely that they are going to replace CFD solvers. So they have a place, but not in CFD. Rather, I would say in maybe enriching experimental results, for example. All right, on this slide, there's another question. What is your recommendation on how to choose data for learning, cross-validation, and testing? All right, so it very much depends on how much data you have. So and also on the dimensionality of the mapping you are trying to create. If you have a low dimensional problem and you have a lot of data, then don't worry about cross-validation and like splitting your data. Just learn it as it is and use all the data, because it's almost impossible that you're going to overfit your model. On the other hand side, if you're doing some like really high dimensional approximation, then I would just follow the typical guidelines. Of course, it is always better if you have more training, if you have more data available, and then yeah, do the typical split. I don't know, validation test and training, maybe 60% for the training, 20% for the test, and 20% for the validation. But there's a lot of freedom in choosing the split, basically. All right, there's something else? No, not really. So again, here I've compiled a couple of links that you can follow and find more resources if you, for example, want to build directly machine learning applications or deep learning applications in OpenFOAM. I would recommend to check out the PyTorch C++ front end, and also, of course, there are nice tutorials on GitHub. So finally, the time is almost over. Let me just thank you for your attention, for the questions you post here in the chat. I hope I caught all of them. If not, you have some minutes left to basically answer those questions. And of course, I also want to thank the organizers. I know we are just the first day into the conference, but I have to say, so far, the organization, the flow of information, like even preparing this training session, this was really superb. This was, I've participated in a couple of online presentations, conferences this year and the last year. And this one here is really outstanding so far. So from the organizational point of view. So thank you very much. All right, now we have a couple of minutes left. 4 minutes I see here in the board. If there are more questions, I can answer them now. If not, you have the option on this platform basically to pose questions later on, and I have the chance to answer them for the next couple of days, of course. Maybe like there was a question I couldn't answer about the SU2 solver. So basically, what I couldn't understand is basically which part of what I explained you want to port to SU2 basically. Where can we find this slide? Could you please provide the link? So if you just go basically to the in my current question box, it's the top link. Basically, it says here are the slides again, and then there's the link of the slides. Okay, doing the same NACA airfoil tutorial in SU2. I'm not 100% sure which kind of output formats SU2 supports. I think I remember that SU2 at least supports output in VTK, and I think there's not yet a VTK data loader online, so to get basically SU2 data into FlowTorch or into Python. But I'm working on that, so this is like on my to-do list because I need it for another project. So it will be probably pushed within the next 2 weeks, I guess. So in the meantime, if you want to just implement it yourself, there is a VTK Python module by Kitware, I guess, and this is like. Oh, there's another recommendation here to load VTK data. You can use the library Video on GitHub. Yeah, so there are VTK is such a popular format, so there are a bunch of libraries that allow you quick and easy access. All right. Python VTK base module is a pain. Okay, I haven't experimented with it so far. Thanks for that information. Maybe I will not use it then. And I will definitely check out this library you posted here, Josh. So thank you very much. Video. I have a look at it. All right, we have about 40 seconds left, so quite good on time. Yeah, thanks again for attending this training session. And if you have further questions, as I mentioned, just post them here. Get in touch. There are plenty of links on the slides, so feel free to get in touch. And thanks. Bye-bye.